fixed point iteration and the bisection method. What we showed in both the fixed point iteration as well as the bisection method cases, both these methods have a linear rate of convergence, and then we took up the fixed point iteration method, and then when we saw that one particular expression gives us one solution whereas the other expression leads us to the other solution. And then we checked back with what we know about the sufficient conditions for convergence, and we observed that those conditions are indeed met as sufficient conditions. What we are going to do in this lecture is essentially to extend that analysis to the Newton-Raphson method. We will look at how fast or what is the rate of convergence of Newton-Raphson method, how we can derive the Newton-Raphson's method from Taylor series expansion, and then we will again go back to Microsoft Excel in order to demonstrate how the Newton-Raphson's method works. Okay. So let us start with Newton-Raphson's. We are interested in solving the nonlinear equation f of x equal to 0. Okay, this is what we are interested in solving. Let us take a Taylor series expansion of f of x around the current guess xi. So the current guess is xi. Okay, so f of x can be written as, I'll just start from this end actually. Okay. So f of x can be written as f of xi plus f dash multiplied by x minus xi plus f double dash multiplied by x minus xi squared by 2 factorial plus f triple dash x minus xi cube by 3 factorial, so on and so forth. It is an infinite series that we are going to look at. Okay. So what this particular expression, what we are going to do is, let us say that our xi is very close to the true solution x. If it is very close to true solution x, then this error x minus xi is very small. If that error is very small, we can then neglect the higher order terms compared to the first order and the 0th order term. So what we will say is that when at x equal to xi, or sorry, at x equal to xi plus 1, f of x equal to 0. So we will make that particular assumption in order to get xi plus 1. Again, f of xi is not, xi plus 1 is not exactly going to be equal to 0. Why it is not exactly going to be equal to 0 is because we have indeed thrown away these higher order terms. So at x equal to xi plus 1, if fx equal to 0 means we substitute this guy equal to 0 and this equal to xi plus 1, and then discard all the terms in that infinite series expression. When we do that, we will essentially get 0 equal to f of xi plus f dash of xi multiplied by delta xi plus 1. Okay, delta xi plus 1 is nothing but xi plus 1 minus xi. Okay, and when we rearrange that, we will get delta xi plus 1 equal to negative f of xi divided by f dash of xi. Okay, or we can write this as xi plus 1 equal to xi minus f of xi divided by f dash of xi. Okay. So, this is essentially our Newton-Raphson's method. Okay. And essentially we have derived the Newton-Raphson method keeping only the first derivative terms in the Taylor series expansion. Okay. So, f dash of xi essentially represents the tangent at that point, and that was the geometric interpretation that we had taken earlier when in the first lecture of this particular module is when we talked about a general curve and trying to use the Newton-Raphson's method for this particular point on the curve. What we said was essentially what Newton-Raphson's method amounts to is drawing a tangent and finding out where that tangent intersects the x axis. And again rewriting the particular Taylor series expansion, and now for the true solution, the Taylor series expansion for the true solution is f of x bar, and f of x bar we know is 0. So, 0 is going to be equal to f of xi, okay, plus is going to be f dash of xi multiplied by x bar minus xi, which is nothing but our ei, plus f double dash of xi multiplied by ei squared, and so on. Okay. So, this is going to be our expression for the Newton for the Taylor series expansion for the true solution. Remember our expression, this particular expression that we had obtained was essentially 0 equal to f of xi, that is the Newton-Raphson's solution. So, what we did was we took this particular guy onto the other side, multiplied by f of xi, and then took this guy again onto the other side, plus f dash of xi multiplied by xi plus 1 minus xi. Okay. So, this is the Taylor series expansion, this is the Newton-Raphson. Okay. Now, what we are going to do is essentially realize that this guy, this particular difference can be written as the difference between the error. What I mean by that is the Newton-Raphson's equation, we are going to write that as 0 equal to f of xi plus f dash of xi multiplied by xi plus 1 minus x bar minus, or so plus x bar minus xi. So, what I have done is xi plus 1 minus xi, I have just added and subtracted x bar over there. This particular term is going to be our e I plus 1 negative, and this term is going to be equal to positive ei. Okay. So, this is what we are going to get in when we substitute, and when we subtract this particular expression from the Taylor series expansion that we obtained over here, when we do that particular subtraction, what we will get is we will get, I will just write the Taylor series expansion again, equal to f of xi plus f dash of xi multiplied by ei plus f double dash of xi ei squared by 2 factorial plus higher order terms. At this stage what we will do in the Taylor series expansion is use mean value theorem in order to replace this particular expression with f double dash of zeta. We can always find a point zeta which lies between xi and xi plus 1 such that this particular expression is exactly satisfied without having to include any of the terms in the infinite series. So what we have done, this is an exactly correct solution, this is not an approximate solution. We have discarded all, we have not discarded all the infinite series terms, but we have chosen zeta such that this particular expression is valid, and you can always, by mean value theorem, you can always find this particular value zeta which is guaranteed to lie between xi and xi plus 1. Okay, so these are the two expressions. The first one we get from the Taylor series, first one we get by manipulating the Newton-Raphson's method. The second one we have got by essentially the Taylor series expansion. We subtract these two equations and we will get, these two guys are going to get cancelled, and we will get f dash of xi is minus ei plus 1 plus ei minus ei minus this particular guy okay is going to be equal to 0. This gets cancelled, we take this particular expression to the left hand side and divide throughout by f dash of xi. So what we are going to get essentially over here is ei plus 1 is going to be approximately equal to minus f double dash of xi divided by 2 times f dash of xi multiplied by ei squared. Okay. Why I have written this as an approximate sign is because we have instead of using the value zeta, we have used the value of xi under the assumption that xi and xi plus 1 do not change significantly. Okay. So what we see is the error at the I plus 1th iteration depends on, has a square root dependence on the error in the ith iteration, and that what that essentially means is that we have a quadratic rate of dependence. Okay, recall what we said in the previous lecture is, what we had said is our ei plus 1 can be written as alpha multiplied by ei to the power eta. In this particular case our eta equals 2, and therefore what we get is essentially what we know what we call as the quadratic rate of convergence, and the factor that is going to determine how fast or how slowly this particular expression converges is going to be f double dash divided by 2 f dash. Okay, so this is the overall criterion for convergence of Newton-Raphson's. Now one of the reasons for popularity of Newton-Raphson's is that you will see that the rate of convergence is much faster in Newton-Raphson's compared to the rate of convergence in the fixed point iteration. Okay, so we will take up the numerical example in Excel that we looked at in the previous lecture, and we will try to solve it using the Newton-Raphson's method. And the same example that we wanted to solve in the previous lecture, 5x minus e to the power x by 2 equal to 0, and then we take the first derivative of this, and then the f dash x that we get is 5 minus e to the power x by 2 divided by 2, so or 5 minus 0.5 e to the power x by 2. Okay, so the first step is the iteration number, and this is what I have been doing since the previous lecture. We will x1, let us start with some arbitrary value, let us say 0.3. Okay. Okay, and our f of x is going to be equal to 5 multiplied by x minus exponential of x divided by 2. Okay. That is what our f of x is going to be. Our f dash of x is going to be equal to 5 minus 0.5 into exp of x by 2. Okay, let us change the font size to 18 and let us write this again. Okay, equal to 5 minus 0.5 multiplied by exp of x divided by 2. That is going to be our f dash of x. X I plus 1, as we had written, x I plus 1 is nothing but x I minus f of I divided by f dash of I. Okay. That is what our x I was really. What that means is equal to x of I minus f dash or f of x I divided by f dash of x I. That is our x I plus 1. Again we can compute our f x, we can compute our f dash x. We have started, and this error that we have is just the difference between that. Okay, and then we just drag this down. Okay, we also drag this particular guy down and we drag this guy as well. Okay. So what we see is essentially starting with x equal to 0.3, we are reaching our desired accuracy very quickly. The desired accuracy was 10 to the power minus 4, we are very close to 10 to the power minus 4 already in the second iteration. X I plus 1, x3 is already fairly low. Now if we compare it with the fixed point iteration that we did earlier, and let us do this for x equal to 0.3, this is what we did in the previous lecture, and when we look at that, essentially we see that we require 5 iterations in order to go to the desired solution, or 0.2236 22368, and in this case it has taken much lesser number of iterations in order to go to the desired solution. Let us start with, say, another point, let us say, which is less than the first solution, and again what we find is we take essentially 3 iterations. Within 3 iterations our solution converges. Our x4 is again the desired solution. So what we have seen is, going back essentially to this particular curve where we plotted f of x against x, when we started on this side we ended up with this particular solution. When we start in this side, again we are ending up with that same solution. Let us increase our x to x equal to 1, and what we see when x is increased to x equal to 1, still we have ended up coming at this solution 0.223367, increased from x equal to 1 to x equal to 2. Again the number of iterations that are taken in this particular case is actually more than the iterations that were required previously, but if you still see the rate of convergence, you see that from error of 2, the error has gone to 0.2, that is almost a 1/10th reduction. Beyond this it is almost a 100th reduction, and beyond this it is almost a 1000th reduction, or maybe even more than that. So this kind of does indicate to us a quadratic rate of convergence if not quadratic, definitely much faster than a linear rate of convergence. When we start, let us say, with x equal to 4, again we get to the same solution 0.22367, and we start with x equal to 7. This is x equal to 8, this is when we get to the other solution. So what we see in Newton-Raphson's method is that when we started essentially with these particular solutions, we ended up reaching this particular guy. When we started with, say, a solution on this side of the curve, we are reaching this particular solution. So when we start with, say, x equal to 6, we will again reach 7.1543. When we start, say, with x equal to 5, again we are reaching 7.1543 as the solution. Okay, and this is a very instructive example where we can now go ahead and plot the error that we get over here. I have just written this particular number so that just for the sake of completeness, and we will just plot these guys. Okay, so iteration number against the error. We insert a scatter plot. Let's see. Okay, we'll do this. These are the various errors. Okay, so this is the plot how the errors change with iteration, as we had done in the previous lecture. When we are doing a log plot, see what happens when we take a better value. Okay, so we don't exactly want to go there. Okay, so this is what we get when we have a particular value starting with x equal to 6, is that straight line would have an approximate slope of -2 in this particular case. So what that really means is that the rate of convergence is going to be a quadratic rate of convergence in this particular example. So nonetheless, when we compare the rate of convergence of this particular method with, say, the fixed point iteration method with the same initial conditions, so if we see the fixed point iteration method with initial condition of 6, it requires approximately 10 iterations in order to reach the desired accuracy of 10 to the power -4 or lesser. That happens in 10 iterations, whereas in case of Newton-Raphson's method, we require lesser number of iterations in order to reach the desired accuracy. Okay, so we have reached the desired accuracy in 5 iterations in the Newton-Raphson's method, whereas we have taken 10 iterations starting with the same initial guess in case of the fixed point iteration method. Another thing that we have observed in the Newton-Raphson's method is when we start off from with an x1 value in this particular part of the graph, we will end up on this solution, whereas when we start off in this particular part of the graph, we will end up at this particular solution. Okay, so this is essentially what we see in the Newton-Raphson method. Now there is a problem with Newton-Raphson's method, and that problem arises when our initial guess is at the maxima over here. What that means is that the slope at this particular maxima, which occurs at around 0. The maxima occurs at around 4.22. The slope of this particular curve is 0, which basically means that this curve is parallel to the x axis, essentially meaning that the curve does not intersect the x axis at any point. Okay, so what we have is if we go back and look at the Newton-Raphson's method expression, okay. So when we derived this, we had assumed that our f dash of x not equal to 0, that is when this particular method is going to work. However, if f dash of x is indeed equal to 0, okay, when f dash of xi is indeed equal to 0, that is when you cannot obtain x of I plus 1. Again, what it physically means, looking back to that particular example, is at the maxima point we have the particular line which is tangential to this curve is parallel to the x axis. So, there is no point of intersection between this line and our x axis, and that is where the Newton-Raphson's method is going to fail. Now, the question is, if this is what we are going to get with Newton-Raphson's method as failing, what is it that we can do? Well, what we can do is at this particular point artificially give a small slope to the Newton-Raphson's method, so that there is some point at which this Newton-Raphson's method intersects. So, the modification for naive modification for Newton-Raphson's method or a straightforward modification for Newton-Raphson's method is that if f dash of xi is approximately equal to 0, okay, then we change the Newton-Raphson's method to xi plus 1 equal to xi minus f divided by f dash plus some value plus some small value beta. So, in that particular case we will write our xi plus 1 equal to xi minus f of xi divided by f dash of xi plus beta, okay, where beta is a small enough number. So, small enough number indicates essentially that we are giving it a slight slope, we are giving the tangent a slight additional slope such that it intersects the x axis at a certain point, okay. So, a very popular method for minimization and for root finding called Leeuwenberg-Marquardt method or LM method uses in a more judicious sense this particular idea, not exactly this particular way of doing it as we have shown over here, but essentially the idea that they use is going to be similar, okay. So, now the question is, now under what conditions is the Newton-Raphson's method for the example that we looked on the Excel sheet going to converge to this solution, and under what condition it is going to converge to that solution. So, basically in a straightforward example of this type, what we will find is when the initial guess is to the left hand side of the maxima, at that particular point the solution is going to converge to this particular value is going to converge to this solution, and when we are on this part of the curve the value of the solution is going to converge to this solution. For example, with a point over here we will draw a tangent, that tangent intersects the x axis at this point. When we then take a tangent over here, it intersects the x axis over here, the tangent at this point intersects the x axis over here, and we are quickly reached this particular solution. Likewise, if we start off with a point over here, this is going to be our second iteration, this is going to be our third iteration, and we have already reached this particular solution. So, when we start off on this part of the curve, we will essentially are going to reach this solution. when we start off with this part of the curve, we will essentially reach that particular solution. The problem, one problem as we had said in Newton-Raphson's method is when f dash of x is indeed going to be equal to 0. There is another problem when we look at the Newton-Raphson's method. So there is another problem when we look at the Newton-Raphson's method, and that problem can be stated perhaps as follows. Let us say a curve is essentially say of this type, and let us say we start off with this as our initial guess, and we might get essentially a tangent that looks like this. This is going to be our xi plus 1, and the tangent that we perhaps draw at xi plus 1 would end up intersecting let us say somewhere over here, okay, and this point again goes back to this. Okay. So what we end up doing is we end up getting caught in an infinitely long loop in which this particular solution throws us to this solution throws us to this solution, and it keeps repeating again and again and again, and we will never really reach our x bar. Okay. Again, this is a very simplified way of looking at this. It's oftentimes what happens is that the solution may go through the 3 or 4 or 5 different guesses before reaching the same initial guess, and it keeps repeating over and over again, and we won't really get a convergence. Okay. And a third set of problems is essentially going to have to do with very slow rates of convergence, and an example for that is, let us say we have a curve of the form f of x equal to x to the power 5 minus 1 equal to 0. Now we know that one of the solutions for x to the power 5 minus 1 equal to 0 lies at x equal to 1, and the curve that we draw is essentially going to look somewhat like this. Okay. And this is going to be the solution x bar, and if we start at this point, we will be thrown at quite a distance away, because the slope is going to be extremely small in this particular case. So we will end up starting, let us say, at a point which is much higher over here, and we will end up coming at this particular location, and then beyond this point, as the iteration progresses, our convergence is going to be extremely slow. Okay. And that is one possibility where our Newton-Raphson's method can run into some problems. So what we will do is we will get back to Excel, and we will see what that problem, where that problem occurs in the Newton-Raphson's solution. Okay. And to solve x to the power 5 minus 1 equal to 0. So what we are interested in solving is x to the power 5 minus 1 equal to 0, and our f dash of x is going to be 5 times x to the power 4. Okay. So this is equal to x to the power 5 minus 1, and this is going to be equal to 5 into x to the power 4. Okay. So, let us say we start with say x equal to 0.5, okay, with after x equal to 0.5 our next value goes at 3.6, from 3.6 it goes to 2.88, 2.3, 1.8, so on and so forth, and it reaches the our desired solution fairly quickly in almost 10 iterations. Let us say we start with x equal to 5 in this particular case. We have finally ended with this particular solution. Compared to the previous case, we do find that in this particular case the rate of change of error is comparatively fairly slower than what we had seen in the previous example, and we take much longer time in order to converge. Now if we were go to x to the from x to the power 5 minus 1, if we go to x to the power say 10 minus 1, in which case our f dash is going to be 9 times x to the power 9. Okay. In that particular case we are going to find that the overall convergence is going to slow down even further. So we make those changes, and over here we have 9 into x to the power 9. Okay. And so as we see over here is that the solution is fairly slow in converging. Let us go to maybe to say 20 iterations. Okay. So when we started with say x equal to 5, the error started at 0.55, and as you can see that the error is decreasing fairly slowly as the number of iterations are increasing. Once the Newton-Raphson's method comes fairly close to the solution, let us say at 1.02 or something like that, then what we find is that there is a sudden increase in the rate of convergence of this of the Newton-Raphson method. So initially the Newton-Raphson method is converging fairly slowly, but when it comes very close to the actual solution, at that time the convergence is going to be rapid. We will again look at this particular example by going even further and taking the initial guess as equal to 10. Our initial error is 1.11. As the number of iterations increase, the error as you see is coming down very slowly compared to the previous cases. The number of iterations that are required are quite a lot. Okay, and at the end of 30th iteration I am quite sure we are going to converge, but we just want to look at how the convergence happens. Okay, so this is the error. From error of 1.11 we have decreased to an almost an error of 0.98. From that we have decreased further to small error values, and if we go lower and lower towards the error, we find that the rate of convergence is fairly slow. Now from this point onwards we will suddenly find that when we come close to the actual solution, the rate of convergence really picks up now, and that is the feature that you will see of all Newton-Raphson's method, is that when we are actually very close to the actual solution, the rate of convergence becomes a quadratic rate of convergence, and when we are fairly far away, the rate of convergence sometimes is going to be slow in the best case scenario, and in the worst case scenario we may not have the system converge to the actual solution. Okay. So this is what we observe in Newton-Raphson's method of in a single variable. So what we are going to do next essentially is to look at multivariable case. We'll essentially cover how to extend the Newton-Raphson's method and the fixed point iteration method to a general multivariable case. we will then take up an example of that multivariable case, and then we will finish off with the nonlinear equation solving part of our lecture of our module. Okay, thank you.